Thank you for inviting to the EC. It's a very good honor for me. I'm Changhwa Lee, and the paper I'm going to be presenting is Fair Prediction with Endogenous Behavior, joint work with Christopher Jung, Sampath, Mallesh, Aaron, and Rakesh. So recently, a lot of decisions are either made by or assisted by algorithms. For example, Amazon had adopted an algorithm that classifies the applicants into high-profile or low-profile candidates. The criminal justice system had adopted an algorithm that classifies the defendants into high-risk or low-risk. Both of these algorithms were backlashed for being unfair across the groups, whether the groups being based on the gender, or minority, or race. With this background, there is a lot of research is going on about how to make the classifications fair. And one celebrity result in this literature is the impossibility result. The result states that any classification rule cannot simultaneously satisfy some of the fairness criteria that we would like them to satisfy, which is to equalize the false positive rates, false negative rates, and positive predictive value. And ever since then, the focus of research has been about finding what kind of fairness criteria that we would like to prioritize and how to achieve this. And to explore this issue, one common approach that people have been employing so far goes as follows. Take the data from the past as given, propose a fairness criteria that is desirable, and then propose an algorithm that attains this criteria, and then test how well this algorithm performs using the data that has been given. One assumption behind all this approach that we find to be uncomfortable is that it has assumed that the data in the past is going to be generated in the same way in the future, no matter what kind of classification is being used. This means that the agents who generate the data will behave the same way no matter what kind of classification rule that they're going to be dealing with. We find this to be troubling because a job market candidates who are searching for a job will behave differently depending on what kind of hiring procedures or classification rules that the firms are using. And the criminals are going to behave differently depending on what kind of classification rules that the court is using. And if you think about this, then you realize that the classification that we design are going to have an impact on the way the agents behave, and therefore on the way that the society and economics behave. So there is a consequential impact on societal and economic consequences made by the choice of algorithms. And these are the points where our paper starts from. What happens to the most effective and fair classification rules once we take these endogenous behaviors into account? And we argue that in our simple canonical setup, one way to characterize the most effective classification is to give the right incentives to induce the right behaviors. And we say this is a very different result from the previous literature, where they didn't consider any endogenous behaviors into account. So let's move on to the model. So let me start by giving you a brief description of our story. There are two agents or two players in our model. One is the judge and the other is the agents. Agents from different groups rationally compares the payoff from the outside option, VI, which is the payoff that he's going to be able to get without committing a crime, and the payoff of the crime, R, and the chance of being penalized with an amount C. And he decides whether to commit a crime or not. Each action he chooses leads to a noisy signal, SI, about whether they have committed a crime or not. Their decisions determine the base rates, the crime rates in this context, in different groups. And this is a key departure from the previous literature where they consider the world without the endogenous behaviors. If the agent's behaviors are given exogenously, then their behaviors are given exogenously, and therefore their base rates are given exogenously. The judge then observes both the agent's group G and signal SI, and then classifies the agent as guilty or not guilty. The judge wants to minimize the average crime rates. So now that I have given you a brief story, I'm going to be defining things more carefully here. So let us start with the agent. The agent I from group G has an upside option value Vi that is distributed according to a distribution dg. He may choose from two possible actions, either to commit a crime or not. Each action generates a noisy signal Si from a distribution Fa, and the distribution Fa is assumed to be identical across the groups and satisfy the monotone likelihood ratio so that the higher signal indicates the higher probability of the person having committed a crime. The judge observes the agent's group G and signal Si, and then classifies as guilty with probability beta GSI. So beta GSI is the classification strategy that the judge uses. Now that we have defined the beta, the classification rule, we can define the true positive rate of the classification, which we denote by TPG. This is the expected probability of the person being classified as guilty, given that the person has truly committed a crime. We can also define the false positive rate for group G, which we denote by FPG, which is the expected probability of the person being guilty, given that the person has not committed a crime. The agent from group G chooses to commit a crime if and only if the payoff of committing a crime is higher than the payoff of not committing a crime. If the agent does not commit a crime, then he first gets the payoff Vi, and then bears the risk of being classified as guilty with probability Fp, in which case he has to pay the fine C. If he commits the crime, then he gets the payoff of doing a crime, R, but then exposes himself to the probability of being classified as guilty as much as the TP, in which case, again, he has to pay the fine C. So agent's decision on whether to commit a crime or not depends on the classification rule beta, which then determines the false positive and true positive rates that he's facing. So this again is a key departure from the previous literature, because the way agents behave is endogenously determined as a reaction to the classification rule beta. Consequently, each classification rule beta results in different current rates. So now that I have introduced our baseline model, which is really simple, I want to take you to our main question, which is that once we take the agent's endogenous behaviors into account, does it change the optimal classification and its fairness properties a lot? And to talk about change, we have to talk about where does it change from? And a natural reference point is the world without the endogenous behavior. It has been observed in the literature that in the world without the exogenous behavior, equalizing posterior thresholds are the most effective and fair classification rule. This classification rule requires the judge to classify the person as guilty if and only if the posterior probability of the person having committed a crime after collecting all available information is larger than a certain threshold, where the threshold tau is the same across all the groups. This classification is fair in the sense that it applies the same threshold tau to all the groups. And once you introduce the endogenous behaviors, the structure of the optimal classification rule changes a lot. And in fact, the most effective classification rule in our environment only cares about giving the right incentive to induce the right behavior. That is, to maximize the disincentive to commit a crime in order to minimize the crime rates. And the adverb only worth an emphasis, because if you go back to the previous slide and think about the world without the endogenous behavior, then the word incentive does not make a sense there because there's no endogenous behaviors. And therefore, incentive was not a part of the discussion when you're designing the optimal classification rule. But now that you have introduced these endogenous behaviors, not only that the incentive matter, but this is the only thing that matters in designing the effective and fair rule. So to understand what is going on there, let us have a look at the crime minimizing classification. The agent chooses to commit a crime if and only if his payoff of not committing a crime, V, is lower than the marginal benefit of committing a crime. R is the benefit of committing a crime. TP minus FP, which is the difference between the true positive rate and the false positive rate, is the marginal increase in the probability of the person being classified as guilty and having to pay the fine because he commits a crime. So let us call this quantity, TP minus FP, as delta. If you increase delta, then the probability of you being classified as guilty is increased once you commit a crime, which increases the probability of the person having to pay the fine, and therefore this decreases the incentive to commit a crime. So we're going to be calling this quantity, delta, as the disincentive to commit a crime. And from the perspective of the judge who wants to minimize the crime rate, will want to set and design the classification beta in a way that maximizes this delta. And if you look at this delta, the disincentive, this only depends on the signal structure, F, and how the judge uses it, eta. But this does not depend on the demographic information, DG. As a result, the crime minimizing classification, the beta is identical across all the groups. This in particular implies that the true positive rates, TP, the false positive rates, FP, and the size of this incentive, delta, are all the same across the groups. So this classification, which is the most effective one, is also fair in the sense that it equalizes these desirable fairness quantities across the groups. And furthermore, any fairness notions that uses demographic information DG are incompatible with the crime minimizing classification. This includes equalizing posterior risk thresholds, which were the most effective and fair classification in the world without the endogenous behaviors. And this also includes the equalizing positive and negative parity rates, which are one of the most often considered fairness criteria in the literature. So this property is interesting in the sense that the demographic information, DG, is useful for classification, but is not really used. Once the actions are chosen and given fixed, this demographic information, DG, is useful for classifying who is likely to be guilty and not guilty, as in the case of the world without the endogenous behaviors. However, if you use this demographic information for classification, then this distorts the incentive of the agents and thereby increase the crime rates. Use this information in order to lower the crime rate, even though they are useful for classification. So this result is very robust as long as the signal structures are identical across the groups. Agents may have different costs and rewards for crime, and agents may not behave perfectly rationally, and for example, may pick a random action with some probability that might even differ across the people. And the signals may be observed at different rates across the groups. All these tweaks does not really change any results. If the signal distributions differ by group, then things can get more complicated, and some of the results get changed. But we can still show that for a large class of the signal structures, equalizing these disincentives, delta, is the only fairness notion that is compatible with the crime minimizing classification. And this is not to say that equalizing disincentives is universally the best solution in the world without the endogenous behaviors. However, this raises the point that incentives matter. If you recall, in the world without the endogenous behaviors, thinking about the incentives does not make a sense, and therefore it was not a part of the discussion in designing the fair and effective classification rule. Or once you introduce the endogenous behaviors, in our simple and natural world, incentive does not only matter, is the only thing that matters in designing the effective and fair classification. So with this observation, I'd like to finish the talk by saying, let's think about the incentives.